Frontiers of Machine Unlearning. This is work done along with my advisor, Professor Ponirangan Managuru, as part of the pre-corp research group at IIT Hyderabad. So let's start with what machine unlearning as a problem is, and then what its motivations are. So suppose you have like a trained machine learning model M, trained using some learning algorithm A on a training data set S train. We use this notation throughout the slides. Uh, and the goal of an unlearning algorithm is essentially to have this unlearning operation that takes the model M, the training data, and SF, which is like the forget set or the data to delete from the training data. And in the end, like it should return a model like M subscript U, which essentially has the influence of this forget set removed, and while maintaining the other knowledge of the original model M. So this is essentially like you can call it like deleting the training data from a trained model instead of just like the training data set itself. So why would one want to do this? Well, the initial motivation of the field stems from the fact that first of all, machine learning models have been shown to leak training data. So for example, on the top right, we have this image where uh, essentially it demonstrates a model inversion attack, where suppose you train a model on a face recognition task, then people have shown that you can reconstruct the training data faces from just the model's outputs, and we can see that it's like a pretty good reconstruction of the original image, which might be like a severe violation of privacy if this like model is released on like a public API or a deployment. And because of these reasons, and the fact that like in general there are like regulations in, for example, Europe, California, etc. One of them is like GDPR, which has the right to be forgotten, which gives the right to be forgotten, where any user can ask like an organization to delete their data at any point. And this could also imply deleting the data from like machine learning models, especially if they're being able to leak this training data. So so machine learning as a field had like privacy-oriented motivations to start with like motivations like biometric applications, sensitive information data sets, like for example, data on cancer patients and stuff like that. And essentially it stems from this privacy setting, and most of the work is on image classification, as you can kind of imagine, since it's like a very privacy-focused, biometric-focused start to the field. So previously, the formulation that has mostly been used is that the forget set is modeled as these independent deletions that are occurring because the user is asking for some deletion request. And then the question becomes that if these deletions are actually like some uniform sample of your training data, what really is the influence of this forget set on your model, which you want to remove? And the way people answer this question to some extent is just like relying on this inefficient gold standard method, which is like if you remove your training data, remove your forget set from the training data and retrain a model from scratch, uh, you get this new model which essentially does not have any influence of the forget set, and this acts like a gold standard for your unlearning procedure to approach. And the only problem being that this is very inefficient. Like these days, we're training models on like extremely large amounts of data, on taking like extremely expensive computation runs. So it might not be a good idea to like retrain your model every time a user wants to delete some data. Now, so what people do to like approximate this goal is essentially that your unlearning procedure should output a distribution of models that's indistinguishable from retraining from scratch. So it's like a relaxation where you don't have that guarantee, but you're trying to like be indistinguishable from the like the perfect algorithm. And empirical evaluations typically do like membership inference attacks, which basically check for the presence of some training data in the model. I won't go into details of this because it's not very important for the work I've done. So overall, the emphasis is entirely on efficiency. Basically, the goal is that like you want more efficient approximations of this gold standard inefficient method of retraining from scratch. So now I'll start talking about our work, which is like the first paper I'll talk about is corrective machine unlearning. This is like a recent work with a bunch of collaborators, and which recently got accepted at the data-centric ML workshop at ICLR 2024. So our motivation for unlearning is like slightly different. So what the question we are interested in is like, can we use these unlearning methods that people have been coming up with to unlearn incorrect or manipulated training data? So I'll elaborate on that a little bit. So first of all, what happens typically, like as you can, like as is illustrated in this toy figure, is that like typically what happens in ML training pipelines today is that you get training data from a lot of different sources, and there are a lot of people, different people who hold like edit access to this data that you're getting for your model, and it's very possible that like it's very possible for someone to manipulate their data in a way that your model performs poorly. These could be like people who don't like your company or something, or like in general want to like have vulnerabilities in your model that they can exploit for like financial benefit or whatever. And so basically some of your sources can have like these like may not be trustable and might have this manipulated data. Now the thing is that like since this data is coming from a lot of different sources, the exact nature of manipulation can sometimes be unknown. So after training you might realize that some source gave you like manipulated data, but you might not have the resources to like go into and try to figure out what exactly the manipulation was, especially because sometimes these manipulations are designed to be imperceptible to the model developers. And yeah, and another key change that comes with this manipulated data setting is that the deleted samples may not completely be IID from the training data, and they're not necessarily all specified by the user. So essentially, you have to do the detection process of finding manipulated data. So I'll come to how that changes things in the next slide. So okay, so first of all, what are the goals of this corrective unlearning setting? So essentially, you're given like some subset. Again, like we'll use the notation SF again. You're given some subset of the manipulated samples, and you want to achieve the following. First, you want to do unlearning well, which is basically improve accuracy on samples from the affected domain. So what this basically means is that the manipulation might be affecting affecting the performance of your model on certain parts of the data distribution. So you might want to like basically the goal is to improve the accuracy on those affected domains, and at the same time you want to maintain or improve the overall accuracy across the whole data distribution. So you don't want your model after unlearning to become like useless on other data distributions. So what this figure illustrates is like, I think the most important challenge of the setting, which is that the prior gold standard of retraining from scratch on the remaining data starts failing in the setting. Why? So for example, let's say, let's consider like a poisoning attack, which is one type of manipulation, where users inject like a trigger pattern in some images, and the model learns that whenever that trigger pattern is present, it has to misclassify that sample. And now the problem is that like these poisoning attacks are very data efficient. Like even with a few, like even with 100 samples, you can essentially like have a reliable poison built into your model, which acts like a backdoor which any adversary can exploit at deployment. Now the problem is that suppose like I manipulated 100 samples in your training data, and then you were able to identify let's say 50 samples, and you used retraining from scratch uh, after removing those 50 samples. The problem is that the other 50 samples still remain in your training data, and the model will still learn the poison and still like be vulnerable to that backdoor attack. So that's why this gold standard of retraining without the deletion set starts failing in this setting, and essentially that's a problem because like as I mentioned earlier, most of the unlearning proposals until now have been approximations to this gold standard, and because of that reason they also start failing in this setting, which we'll show in our experiment. Uh, yeah. So moving on. So I'll quickly highlight some differences from the traditional privacy-oriented unlearning setting. First of all, the goal changes completely. In the privacy unlearning setting, you typically are trying to remove correct data, but which you want to privatize. So you're losing some information. Whereas here we're trying to remove wrong data. So that should actually improve the accuracy of our model. Another complication this introduces is that the clean labels of your data to delete are unknown, which can cause some issues in like picking the best model based on a hyperparameter search and so on, because you don't have the perfect validation set. Yeah, and then like I said, accuracy typically drops in the privacy setting where you're losing correct information, whereas here we want the accuracy to increase, or at least on certain domains. And the second big difference is that like the amount of information available to you is inherently different, because in the privacy setting we were assuming users are telling you what data to delete. Here you have to figure out what data to delete on your own, and that basically leads to like partial manipulation sets being known for deletion, which is the complication I was discussing earlier. So the next big difference, which is more like an implication of the previous difference, is that retraining from scratch on the retained set is no longer sufficient, which I motivated in the previous slide. And overall, there is like we all like while all this makes the problem harder, there is one thing that does make the problem easier, which is that you don't have a privacy requirement on the forget set anymore. So you don't need like theoretical guarantees on privacy, or at least it's less important than the privacy setting. And you don't need to evaluate using membership inference attacks, which were essentially just checking whether a sample is in your training data or not. So now I'll jump to our experimental setup. We test two types of manipulations. There are like a lot of different types of manipulations we can do. We pick these two because we think they represent like two distinct kinds of attacks that can occur. The first manipulation we pick is like a feature and label both being manipulated. So for example, this can occur when, suppose to train your model, you're creating data from web pages. People have shown before that adversaries can manipulate both the images and the labels. So, for example, Carlini et al. Showed like an attack on Wikipedia data. So, if you're scraping from Wikipedia, they showed that you can efficiently pull off like poisoning attacks in the wild. And essentially, yeah, so the poisoning attacks makes models vulnerable to backdoors unknown to the developers, because typically the trigger pattern used for the backdoor is not known to the developers and is imperceptible, so it's hard for them to find. And like reliably in the presence of that trigger pattern, the model starts misbehaving. So empirically, we use the bad net poison, which is like a classical poisoning attack. It's very simple, and essentially what happens is that you add like these 4 pixels at the bottom right of your images, let's say, and mislabel them as like a certain class. We pick class 0 without loss of generality mostly. And then like the metric that we're trying to measure for our unlearning is computing accuracy on like unseen samples with the poison trigger. So basically, after the poisoning attack, the original model will have very low accuracy on samples with the poison trigger, and after unlearning, you expect the model to become as good as a normal model without the poison on the poison samples. And the second manipulation we test is a label-only manipulation. This is a test introduced in our earlier paper. So it's called the Interclass Confusion test, where basically the motivation for this is that essentially, like in a lot of cases, what happens is you have your own data, but you hire external annotators to do the annotation for you. And sometimes because of like either systematic biases, they can confuse samples from 2 classes, or because like you gave them wrong annotation guidelines, or maybe they actually want to hurt the performance of their model in a more adverse circumstance. So essentially what happens in this test is that we take, let's say we take 2 classes. Here, for example, I've illustrated cat and dog. Now, if we take some cat samples and mislabel them as dog, and some dog samples and mislabel them as cat, the trained model becomes confused between cats and dogs to quite an extent. So once you try to unlearn these manipulated samples, the hope is that the model's confusion between cats and dogs would reduce. So that is like essentially the metric we're measuring and the goal for unlearning here. So I'll straight away get to the results. So on this slide, essentially I have like the main unlearning results across both manipulations and across 2 datasets, CIFAR 10 and CIFAR 100. So on the x-axis, we're reporting like the fraction of the manipulated set that is known for deletion. We're varying this from 0 to 1 at intervals of 0.1. And on the y-axis, we have like the clean label accuracy on the affected domain, which is what we want to increase after unlearning. Now, we test like a bunch of state-of-the-art popular unlearning methods. So first of all, the gray line at the bottom everywhere is like the no unlearning, which is basically just the original model. Then we have the bad teacher method, which is the blue lines. And this is like a IEEE 23 paper on unlearning. Then we have the CF method, which basically does catastrophic forgetting on the forget set, essentially fine-tuning the model on the retained data. This is a method we introduced in our past work. And then we have exact unlearning, which is retraining from scratch without the data being deleted, previously considered like a gold standard in unlearning. Then we have SST, which is like a IEEE 24 paper. We have Scrub, which is a NURIPS 23 paper. So yeah, so yeah, these are basically all like very recent methods that we benchmarking here. So now let's get to the results. Let's first look at the left column, which is the poisoning plots. So in both plots, what you can clearly see is that, first of all, let's look at the orange line, which is the exact unlearning method. We see that until like 80% of the manipulated set is detected, it's basically performing no useful unlearning for us. And that's to be expected because, like I said, the poisons will still exist in your training data. So if you retrain again on it, the model will still continue to learn the poisons. And because of this, we also see that CF and Scrub, which are essentially like efficient approximations of this exact unlearning method, they also suffer from the same problem where until like 70-80% of the data to be deleted is known, they're still not being able to unlearn well. The BATI method does pretty poorly because it's just like optimized to move away from the old label, but it doesn't give you any it's basically doing gradient descent on the old label, which essentially leads to like degradation in performance in general. The only hope we see is that the SST method, even with like just 10% of the data to be deleted known, is able to like recover the accuracy like very much. So it's essentially like a quick step function jump on the unlearning accuracy. So this shows us hope that like this setting is fairly tractable, that you can perform corrective unlearning even with like a partial manipulation set. So with this, we jump to the next setting, which is like the interclass confusion setting. And immediately the first thing to notice here is that the red line, which was SSB, which was doing well in the poisoning setting, completely fails. And there are fundamental reasons to this, which I can come to later if anyone wants to know them. But what we see is for the other unlearning methods like U, CF, and Scrub, we see like gradual improvements as more of the deletion set is known, which is pretty decent, though I guess like ideally you would want something like the SSB behavior on the left plot for poisoning. So yeah, that was the unlearning results. Now coming to the overall utility of the model after unlearning, well, most methods, essentially in this table we're reporting the change in accuracy after unlearning using these methods. For most methods, this is like slightly positive or like near zero. But for the SSD method, which was working well for the poisoning setting, we actually see there's like a like 4 to 10% jump, 4 to 10% drop in the model's overall test accuracy, which is pretty bad because clearly your model is like losing general utility and its original knowledge. So there's like clearly scope for improvement there. So overall, what we see from our results in this paper, well, first of all, our old gold standard exact unlearning fails at less than equal to 80% data being known, which leads to most methods also like kind of failing. And this setting is tractable because SST shows some limited success on poisoning, but it fails at IC, and also has a drop in accuracy, which overall shows that like there's a lot of scope for designing better corrective unlearning methods. And overall, we think like that this work is just the start in this area. Like we use very simple manipulations because they gave us like they clearly showed that existing methods are insufficient, but there's clearly scope for like much stronger tests, which could include using just better poisons that came out more recently. Ideally, you would want to do adaptive attacks, which know the unlearning procedure beforehand and then try to show its weaknesses. And then we focus on the supervised image classification setting, though like I think the same ideas can apply to like self-supervised learning or language learning, and it would be good to check that out. We also assume that all the deletion samples known to us are actually wrongly labeled. So technically, there can be false positives when you're doing this detection of like manipulated samples. But yeah, we don't model that in our experiments. And overall, I think like this opens up scope for a bunch of interesting theoretical analysis, especially like under what conditions can we maybe infer the whole manipulated set from like a partial deletion set, and which manipulations is this possible for, how much data do you need, and so on. Yeah, mostly, yeah. Okay. Right. Okay. It'll be more robust to poisons. Yeah, yeah, that would be. Yeah, yeah, yeah. We showed that they're insufficient for removing manipulated data. That was the main insight. Yeah. Okay. Now I'll talk about the second work that's part of my thesis, which is essentially a different application of unlearning. So here what we're trying to do is we're trying to unlearn dual-use domain knowledge from large language models. This is work done along with the Center for AI Safety and recently accepted at ICML 2024. So the motivation for this project is that like recently the White House released like an executive order saying that for these powerful large language models that are coming out these days, they should basically not enable or make it easier to design, let's say, harmful weapons, for example, like chemical weapons, biological weapons, or even cyber attacks, which are like fairly plausible as they like approach like a lot of like knowledge that is not available to like common humans unless you're like an expert in that field. So yeah, so the idea is that can we like the risk here is that language models might lower the barrier of entry for non-experts to cause harm, and we want to basically see if we can unlearn this dual-use knowledge from, let's say, cybersecurity domains or like biosecurity risks and so on. And the motivation here is that like typically what people have been doing with large language models to like handle this risk is refusals, where like if you give it a prompt, it will reply that I cannot answer this query, it's harmful, whatever. The problem is that these refusal fine-tuning, like refusal alignment techniques, are prone to jailbreaking, where like with sufficient adversarial prompting, you can still get the model to output whatever it was and not refuse. Now, the hope here is that if the model doesn't have knowledge about a certain bad thing in the first place, then it won't be able to leak this thing. So it's essentially drawing an analogy from like chemical security, where you're like, if you don't store toxic chemicals, you can't leak them. So yeah, So in fact, like in our work, we do show like some initial results that like, yeah, sure. So we're trying to unlearn domain knowledge from like dual use areas, such as like, let's suppose like there's some knowledge that helps you create bioweapons or create cybersecurity attacks and stuff like that. So it's essentially domain knowledge removal with unlearning. Yeah. So the first thing we do here is like, the first thing you need to do this sort of a study is designing a benchmark for like cybersecurity, biosecurity, and chemical security. So that's something we like. Essentially, the Center for AI Safety got some experts to create this dataset for us, which has like 4,000 MCQ questions on across these 3 different areas. And essentially, the goal is that uh, we should be able to remove some precursors to the knowledge needed to cause these harmful attacks on like public infrastructure or whatever. So I'll focus a little less on the benchmark, apart from the fact that it's like a 4-way classification MCQ benchmark, because my work was more on the unlearning and evaluation side. So I'll skip to that. So first of all, I straight away jump to talking about the unlearning method we propose in this work. So this is something called contrastive unlearned tuning. And the idea essentially is that in some previous work, we had shown that like you can steer the representations of a language model to behave in certain ways. So you can like essentially add a toxicity steering vector to the internal activations, such that like if you subtract that vector, the model becomes less toxic in its output. So we use that intuition to some extent. And here what we're steering is that like we're basically steering the model from expert knowledge in say biosecurity to novice knowledge in biosecurity, because what we found was that if you prompt the model with you are an expert in biosecurity, it will give you higher accuracy on our benchmark. Whereas if you prompt it with you are a novice in biosecurity, it will basically give you random chance accuracy. So yeah, so essentially what we do is we, let's say, take some layer L of the model, of the frozen original model. We collect the activations for the you are an expert prompt across like some documents we scraped from the internet related to biosecurity. And similarly, we collect its activations after prompting it with you are a novice in biosecurity and like answer this question. Uh, so we collected these 2 sets of activations, and now what we're doing is we're fine-tuning the model such that first of all, we want to on the left side, as you can see, what we want to do is we want to shift the activations towards the like novice minus expert direction, and essentially this forms our loss where like we have our original activations, we add this novice minus expert term, and we fine-tune the model such that like its representations go towards that by minimizing the MSE between these activations. And now this has one possible side effect, which is that your model will lose its general knowledge because the activations will just become bad overall. So to make sure we preserve old knowledge, what we do is for like a retain set corpus, like, we use like wiki text as the retain set corpus. We try to ensure that the model's activations at the same layer are similar to the original model, such that it retains the knowledge of the original model. So essentially, we try to do this surgical intervention where on the biosecurity prompts, it's like losing its knowledge, going towards the novice, but on the remaining prompts, it's like staying there. Okay, so coming to the results. So first of all, let's talk about the plots on the plot on the top. What we're testing here is like we performed the biosecurity and cybersecurity unlearning simultaneously, and now we're testing the model's accuracy after unlearning on the bio benchmark, the cyber benchmark, and also MMLU, which is like a general knowledge benchmark, to make sure we retain general knowledge. And what we find is that clearly the base model had like 60% accuracy on the bio benchmark we designed, but after unlearning, it has like around 30% accuracy. And on the cyber dataset, it actually has like random chance accuracy, which is exactly what you want, which tells you that it kind of is not giving you that information on these MCQs anymore. And on MMLU, we see a 1 to 2% drop in the accuracy. These results are all on Zephyr 7 billion, which is like a 7B LLM, which performs, I think, like at the time of these experiments, it was the best LLM in the 7B category of models. And on the right, we're comparing like our method to a bunch of baselines. So we use like the Scrub and SSD baseline I talked about earlier. We adapted it to the language modeling setting. And there's also a language modeling unlearning method that was proposed earlier by, I think, the TikTok research group, essentially. And essentially what we found is that like these other methods, they reduce the accuracy on bio and cyber much lesser, and at the same time have much larger drops on general knowledge, which is MMLU. So overall, our method like clearly does better in unlearning and also retains the prior knowledge more. So this is like on the output space of the models. The next thing we wanted to test was that maybe the model is just like not giving us the outputs, but still has the knowledge in its internal representations. So what we did was we built like we essentially trained a linear probe on internal representations of the model across layers to do this 4-way classification task of the benchmark. And what we found was that again, like the dashed line on these two plots at the bottom are the original model, the base model, and the solid lines are the unlearned model. And we see that clearly the original model, like we are able to extract the MCQ performance from the internal layers, but after unlearning, even from the internal layers, we're not able to like learn a probe that does this MCQ classification, which kind of gives us a strong sense that like we have scrubbed the knowledge off from the internal representation as well. So overall, I think like this is a fairly good start to like this dual use unlearning domain. But I think there's like still some like limitations of future work to take care of. The first hardness we found in this like setting was that this unlearning utility trade-off is like hard to characterize, because what we found was as models unlearn more, their general utility also keeps going down. So ideally, you want something like on the plot on the left, we're reporting like the general MMLU accuracy on the x-axis and the drop in WMDP bio and cyber knowledge on the y-axis. You want a higher drop as more unlearning. So we see that like, ideally you want your method to be like a Pareto frontier on the existing method. And we see that for at least our method, like it's always on the top right across hyperparameter runs, whereas the other methods are like, clearly they're losing a lot of utility as like, clearly they need to like much less unlearning as the utility of the model is maintained more. So that's like one caveat and hard point about like evaluating unlearning procedures in the setting. The second hard thing we found was that unlearning can have ripple effects. This is something that you might expect, which is that like so when you unlearn, let's say like cybersecurity, offensive cybersecurity knowledge, you also lose like college level computer security knowledge, which can be helpful in like building defenses against cyber attacks. So there is like this ripple effect of knowledge that gets unlearned in the process of trying to remove harmful knowledge. And we found that like in our experience, it's very hard to like draw a thick line between these two and separate them. And so basically we found that like there is like a decent drop in CS knowledge of the model after doing our unlearning. We also find like a small drop in college level biology knowledge. We found a significant drop in virology knowledge. So overall, unlearning has these ripple effects, and it's like hard to characterize as like technical people where you want to draw the line. And we might need like policy or like other supervision to be able to draw these trade-offs. So some other like limitations of the current work. First of all, like on the right, you can see that what basically we found is that like we did this unlearning, but you can always relearn the knowledge back. And this is a problem with like open source models, because there's no point of doing unlearning on the open source model because people have data access, they can find you in the knowledge back. At least like our kind of work can help with like black box access, API access models where people don't have access to the weights or can't find you in the model. But we clearly see that you can get the knowledge back if you can find you in the model. The second thing is that like the unlearning, after unlearning, like it is possible maybe that if you change the prompts a lot, maybe do like some adversarial prompting, you can still get the knowledge back. So we did test this out a bit, like we try to jailbreak the model to reveal the unlearned knowledge with the GCG attack, which is like a very popular attack that came out 1 or 2 years ago and has been used as a standard in jailbreaking literature. And we found that we weren't able to use GCG to get the knowledge back, but I think like there's still scope for like more rigorous evaluations of adversarial prompting. And this can also happen like under natural distribution shifts, like if you change the language, maybe the model starts revealing the knowledge back because the unlearning was only done on the English one. So that's the end of that project. Overall, I think from my thesis, like some salient lessons that stood out were that different unlearning tasks can have different requirements, and overall they might require like different methods. So this is, I think, the field was mostly focused on privacy when I started, and I think partially because of our work and some other work that's been going on, I think now people have started looking into these other applications of unlearning. And overall, there's like still scope for like more principled evaluations, which like keeps being shown because like I said, like, we don't know whether unlearning is robust to adversarial prompting and stuff like that. So yeah. And then I think one interesting direction for unlearning till now, it has mostly focused on like these IID datasets where like you training like a language model or like an image classifier where you assume the training data is IID. But in some settings, for example, in like graph neural networks, what you find is that unlearning a certain node will have an effect on its neighbors, and the data is not IID anymore. So it could be very interesting to see what implications unlearning has in these non-IID settings. With that, I'd like to acknowledge some people who have really helped me throughout my thesis. First of all, my advisor, Professor Peter, for his unwavering support. Ameya Prabhu, who was a collaborator since the beginning on this unlearning work, and he's been an excellent mentor throughout. Sajas Vaduguru and Shyam Gopal Karthik for constant feedback and advice throughout the last year. And some collaborators and friends, Nikhil, Shashwat, and many more who I don't have space to thank in this side. And yeah, with that, I'm open to questions.